Hi all, today we discuss the the remaining portion of section 4.3. In that we start with a theorem, first derivative test for local extrema. Suppose that C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing C except possibly at C. So that means f need not be differentiable at C. Still we have this result. If f dash changes from negative to positive at C, then f has local minimum. And the second condition, if f dash changes from positive to negative as we move through this C, then f has local maximum. And if f dash does not change sign at C, okay, then f has no local extrema at C. That means no local, neither local maxima nor local minimum at C. So this is what we call the first derivative test for local extrema. Now we can prove the first part. Since f changes from negative to positive at C, you can find out two numbers a and b such that this f dash has the sign f dash of x is always less than 0, that is f dash is negative whenever this interval a comma c. Okay, for all x in this interval we have f dash x less than 0 and f dash x is greater than 0 for all x belongs to c comma b. This is the meaning of f dash changes negative to positive at C. That means when in the left hand side of the C, you can find an interval at which this f dash x is less than 0, and you can find out an interval in the right hand side of C. There we have f dash x greater than 0. Now this implies if we choose x belongs to AC, we have uh, f of x is here we have derivative is negative. Derivative is negative means the function is decreasing. So here we have function is decreasing means whenever if we choose x belongs to this, we can get this x is less than C because x lies in this interval, implies f of C is greater than or equal to f of x because f is decreasing. So this value has the function has the maximum value or the greater value at C than this x, and this implies for x belongs to CB, we have x is greater than C because x lies in this interval, and here we have derivative is positive. Derivative is positive means function is increasing. Then we have the same result follows. F of x is always greater than or equal to f of c. Here we have f dash x is less than 0, then this x less than c implies f of x is greater than or equal to f of c. Okay, because here we have the decreasing nature, f dash x is less than 0, so this f of c should be less than or equal to f of x. This is the idea here, because this is decreasing. So in any case this f of x is greater than or equal to f of c, so this f of c is a point of minimum. So this implies in the interval a comma b, you can get this f of c is the minimum value. So f of c is the local minima for all x belongs to the interval a comma b. Okay, so this shows that x equal to c is a local minimum. Similarly, for the second case, this you can find a and b such that f dash x is greater than 0 in the interval x belongs to AC, and f dash x is less than 0 in the interval c comma b. So this implies x less than c implies f of x less than f of c. That is because here we have f dash x is greater than 0 rather than less than 0. So we have increasing nature in that interval, that is x less than c, then the same inequality follows. But in this interval we have negative sign for this derivative, then the function is decreasing. Then whenever when x takes from this, we can say that the c is less than x, implies f of x is less than f of c, because this is less than or equal to f of c, because this is decreasing nature. So from these two you can say that the c is point of local maximum. That means f of x is always less than or equal to f of c for all x belongs to the interval ab. Okay, so this implies x equal to c is a local maximum. So this shows that 2 is also true, and if f does not changes the sign, then you can get one side we have this result, and another side we have the reverse inequality. So that at that point c cannot be considered as a point of local minima and local maxima. So that proves theorem 3. So first derivative theorem is proved. Now we discuss this problem. Find the critical points of this function f of x equal to x raised to 4 by 3 minus 4 x raised to 1 by 3, and identify the intervals on which f is increasing and decreasing. And the final question is find the function's local and absolute extrema values. So for this we start to find the critical points by calculating the f dash x. What is f dash x? F dash x is 4 by 3 x raised to 4 by 3 minus 1 minus 4 times 1 by 3 x raised to 1 by 3 minus 1. So that is equal to 4 by 3 x to the power 1 by 3, that is 4 by 3 minus 1, that is 1 by 3, minus 4 by 3 times again x to the power minus 2 by 3, that is 1 by 3 minus 1, that is 2 by 3. So you can simplify this as you can take this 4 by 3 out, then that will be x raised to 1 by 3 minus 1 by x raised to 2 by 3. X raised to minus 2 by 3 can be written in this form, that is equal to 4 by 3 times when you take the LCM of this, then x raised to 1 by 3 into x raised to 2 by 3, that is x raised to 3 by 3, that is x raised to 1 minus 1 divided by x raised to 2 by 3. This is the LCM. Now we have, in order to get the critical point, we need to equate this f dash x equal to 0. That implies 4 by 3 times x minus 1 divided by x power 2 by 3 equal to 0. This implies x equal to 1. So the only possible critical point is 1 from this f dash x equal to 0. But when you consider the derivative of this function, at the point x equal to 0, this function is not differentiable, as in the denominator we have x raised to 2 by 3. So the critical points are x equal to 0, at which the function is not differentiable, and x equal to 1. So these are two critical points. One is x equal to 0 and one is x equal to 1. Okay, now this is x equal to 1. So these are two critical points. So this divides the whole real line into three parts: minus infinity 0, then 0 to 1, then 1 to infinity. Now you take a point on this interval, say minus 1, and evaluate this f dash. When you take x equal to minus 1, you can say that this numerator is this is minus 2 and divided by minus 1 raised to 1 by 3, that is positive. Then because this is x raised to 1 by 3 whole raised to 2, that is x raised to 1 by 3 is again minus 1, minus 1 whole square is 1. So we have this is negative, here we have f dash is negative, then this is decreasing, here we have decreasing nature, and we take a value in between this 1 by 0 comma 1, and you can take any of value from this 0 comma 1. We can say that this is again negative and this is positive. So we have f dash is again negative value, this is negative value, this is decreasing, and take any value between these two greater than 1. When x is greater than 1, the denominator is positive, and as well as this numerator is positive. So here we have f dash is greater than 0, so this is increasing. Now we can divide our interval as 3 points. This is 0 and this is 1. Now we have these intervals. Now we can say that here we have f dash is less than 0. So this is f dash is negative less than 0. Here we have greater than 0. Here we have f dash is again sorry, this is less than 0 again here, and here we have f dash greater than 0. So here is decreasing and decreasing, here we have increasing. So we can say that when you consider the critical point x equal to 0, there is no change in the derivative, because derivative is negative here and here also negative. So x equal to 0 is a point, there is no local extrema at x equal to 0. But when you consider x equal to 1, the left hand side we have decreasing and right hand side it is increasing, that is less negative to positive. So that is the first case. We can say that this function has a local minimum at x equal to 1. So f of x has local minimum value at x equal to 1, because at the point 1 we have left hand side we have the negative derivative and right hand side we have positive derivative. So this shows that the local minimum value is f of 1. The local minimum value is -3, but it has only one local minimum, so therefore it is also absolute minimum value of f of x. Okay, that is -3. That is at x equal to 1. So this completes this problem. Now with this we complete the section 4.3 as well as the module 1. Next lecture we will discuss the second module, which consists of the concepts of partial derivatives.